chapter 7, sampling, for this lecture. As I said, this is slightly different from what we have learned before. This is does not have much transform. Of course, we are using a part of transform, but not really transform. Oh, you have shirts? Aren't you cold? Aren't you cold? Yeah. No? Okay. Do more exercise on that. All right, so let's continue. So let's talk about the sampling theorem. Sampling is a way to, converting from this continuous time signal to discrete time signal. That's the sampling. So if you see this example shown in the picture we show in the beginning of the lecture, say that this is continuous time signal. So if you let's compare their value in x-axis and y-axis. In x-axis, the value is almost infinite. The number of value is actually almost infinite. They are continuous. The value in y-axis is actually also continuous. So this is continuous signal. Sometimes people say this is analog signal. This is discrete time signal, which is we pick up values in continuous time signal. We pick up values from continuous time signal having certain time spacing. So in case of time domain, which is x-axis, this is discrete. We can count the number. In y-axis, the value of y-axis, both of them are actually continuous. So what we talk about discrete signal is we often refer to as discrete time signal. They are discrete in time, but we are not talking much about discrete in value, discrete in y-axis. We do not talk about it. If, as I explained in the beginning of the lecture, if they are discrete in a y-axis also, that signal, we often refer to that as digital signal. So sampling is actually pretty straightforward. We have already learned about it. Sampling is, what I talk about here is from continuous time to discrete time, how to convert from continuous time to discrete time. We pick up values at certain spacing in time. That's what we convert from continuous time to discrete time. Those process is called sampling. Okay? Sampling is what? Sample is what? Sample, if you go to E-Mart, or if you go to supermarket, and if you go to the food court, there are several lady wearing a hat and grill a sample for you, right? Those sample is what? They take something, some small portion of things from a large bag, like the frozen food. They take out some of them and make a sample for you, right? Sampling is similar to that. They picking up a few of it from a large portion. That's why we remember about sample, right? So you can think in a similar way. Say this large portion, which is actually almost infinite number of values in y-axis. We pick up few of it. Discrete time signal. That's a sampling. There's one rule over there. Sometimes people may think that, okay, I want to pick this value. I want to take this value. I want to pick this value. So that the process of picking is sometimes a bit ambiguous. Of course, there is some control or some theory doing not equally spaced sample. There's of course theories like that. But basic theory over here is we try to have a rule that we pick up samples not randomly, but having equally spaced in time. So we are equally spaced on time. We pick up values at like we wait for 1 second. So 0 second, 1 second, 2 seconds, 3 seconds. We pick up values. That's the sampling we are talking about in this lecture. All right, let's go. So the major goal of this chapter is talk about Nyquist theorem. Before we go there, why we have to consider the sampling. Let's have an example which is shown in our textbook. So This is the one example showing that there's three different graphs. There's three different graphs. Say that there is the black solid line, thick solid line is x1, x2 is those dots, and x3 is those those thin solid line over here. Of course, these three signals are totally different signals. We know that. However, when you pick up samples by a spacing of t, so if you happen to pick up some values, say they pick a point here, after t they pick up another point, they pick up another point, they pick up another point, they pick up another point. Actually, these points are overlapping. This is a very exaggerated example. However, what you see after sampling is you only see that you have a data like that in time domain. Of course, there is a R like this, equally spaced t. So you may consider that x1, 2, 3 maybe is the same signal, but actually, you never know that they looks like here, and sometimes they may look like this. I don't know. So how we can solve this problem? How we can find the real data more realistically? So we are picking a data by spacing of time t, right? So say that you are picking up data for every 10 seconds. One way, so the way they looks like, why they are different? Because in here and here they are the same, but between them they are different. So one way we can find out the real data is what if we pick up a data here, 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 for example. So if we short the spacing, if you make the spacing short, then we can have better tracking of the original data. Is it right? That's right. So in this example, I would like to emphasize two things. First of all, sampled data. Sampled data is inevitable in many cases. What we can see here is only discrete in time, data in discrete in time. We cannot have a data between them. But the original data which shown as red and yellow over here, may be different, even though the data point we are picking is the same. One way we can resolve this issue, we cannot completely solve this issue. However, one way you can resolve this issue is picking up data final way. We have more data to find out the original value. That's two things we are talking about, which is pretty straightforward. If you have more data, then you will have more accurate estimation what the original value. That's right. So keep in mind, if you have more data, which means we have a narrower spacing in time. So what we mean here is, this is t, spacing is t. So what we have to do is reduce t, right? In case of frequency-wise is what? In case frequency-wise is what? Basically t over 1. So frequency-wise, we have to increase the frequency. So we will learn about this one later, Nyquist's theorem. Nyquist's theorem here is at least 2 times larger than the signal's frequency. We have to do the sampling. So this frequency is the pair related with the time interval of when we are sampling, right? So this one is called as sampling frequency. Frequency should be larger than at least 2 times larger than signal's frequency. That's a basic rule called Nyquist theorem, which we talk about that a few pages later. So keep in mind, we have to increase the frequency. If frequency is not enough, then we cannot have original data. That's the Bayesian rule over here. So let's think about how we can build discrete time signal. So this is our let's say that this is our continuous time signal, and how we can pick values at certain time. Well, of course, we just let the system know that, okay, let's grab the value, wait for a certain second, and then pick a value. That's the one way we can do that. But systemically, what you can do here is you multiply. Let's think about the convolution. If you have continuous time signal, which is xt, multiply by an impulse, which is delta function space by nt, which n equals minus infinity to infinity. So what is this signal? So what is delta t? In time domain, we draw when time was 0, there's a delta t, right? What is delta t minus large t? Number 1, number 2. Number 1. Number 2. Right? Number 2. So this is spacing. So likewise, if you have t minus 2t, then we have impulse in 2t. If you have t plus t, then you have over here. So we call this one as impulse train of impulse before, right? So this one is impulse train, as you can show in the figure over there. And then when you try to relate two signals, we usually use convolution, right? When you relate two signals, say that, okay, this is our system response. You apply a signal, then the output comes in. Those output is given by x convolution h. That's why we have conducted exercise by far. What if we do a multiplication? Instead, y equals x multiplied by h, for example. So this is what they say. This is just simply multiply. That's not do the convolution. Just to multiply that. Then what happens? This impulse train are equally spaced by t, large t, and amplitude 1. Of course, you know that when they go to infinity small, they go to infinity sometimes. So just how to say, systemically y, if you multiply x by this impulse train, just multiply it, then this will be multiplied like this. This value is multiplied like this, and then displayed over here. This one is multiplied by this, which is same to the amplitude of this, and displayed at here at the same time with this. So once those two are multiplied, they were shown as arrow like that, following the amplitude of this continuous time equally spaced by t. So one way we can do the sampling is to simply multiply by impulse train. That's a systemical way how we can do that. So this is how we do it. This after sampling, we can tell that this one refers to the timing. So after multiplication, they are equally spaced. They're equally spaced. That's what they mean by delta over here. What's the amplitude? What's the error amplitude? Amplitude of this x at this timing. The amplitude is same to here. This amplitude is same to the amplitude of x at this timing, right? So how we can define the amplitude? So we can say amplitude at certain time. That's their amplitude. But what is the time? Nt. It can be x large t, x2t, x3t. So amplitude at certain time is their amplitude, and this one gives you idea that the spacing of them. So after doing multiplication, there will be a train of impulse having an amplitude of x. That's what they do after sampling. Before we move on, question? Nope? Too easy? So, in frequency domain, let's think about some frequency domain signal. When you do Fourier transform, then they will be given as x j omega, x p j omega, and this multiplication becomes what? This multiplication becomes what? So in Fourier transform, multiplication, convolution in time domain becomes multiplication in frequency domain. Likewise, multiplication in time domain changes to convolution in frequency domain. Is it right? But so they will change to a kind of convolution. Say that right. xj omega. We should use theta because we need new variable. And there's another. So transform of this. They will change like that. So say that this transform is. Say that this one's transform is j omega. Then they will become, because it's convolution, we have to pick a new variable. And one of them leave like that. One of them omega minus new variable. That's the convolution. And in the one thing different is convolution in continuous time. You should have this scaling factor. That's one of the difference we talked about before. So this one's Fourier transform is shown in here, which is pj omega equals this one. Those are their Fourier transform. So in short, when you do the sampling, when you change continuous time to discrete time, we multiply by impulse train to get a sampled value at equally spaced t in time. Now we change to frequency domain. To go to frequency domain, we need a Fourier transform. After Fourier transform, they become like that. But this multiplication actually becomes a convolution, which is they given like that. And this one, which is a Fourier transform, they will look like this. However, let's take a look at it in frequency domain. Continuous time Fourier transform. We are doing the continuous time now, right? We're not talking about this. In continuous time Fourier transform, they are periodic or not periodic in frequency. I asked this question many times. So, continuous time Fourier transform, they are not periodic in time. Are they periodic or non-periodic in frequency? Nobody tried to make eye contact with me, I think. So, what about discrete time? So first of all, over there, x is our original signal before multiplication, which is continuous time. After multiplication, they change to discrete time signal, right? So x over there, before multiplication, they are continuous time signal. After multiplication, they are sampled, so they are discrete time signal, which is called xp. So x over here is continuous time signal, so their Fourier transform is continuous time Fourier transform, which is not periodic signal. That's the reason they have things like this. After Fourier transform, after multiplication, xp, which is discrete time signal, so their Fourier transform should be discrete time Fourier transform, which is periodic in frequency. That's the reason in here it looks like that, in here it looks like this, because they're repeating. And we can also think that all right, this one is actually same to the impulse train in frequency, equally spaced by omega s, like this, spaced by omega s, having some scale factor over here. And then if you multiply and do the integration, if you do the convolution between them, how you feel? So from here, this one began to scan, this pole began to scan, following this amplitude, which is this one comes in, and then this second one comes in and began to scan, which is shown like that, and third one comes in and began to multiply by this amplitude, which is shown like that. You can think in this way also. So you can individually think that x is continuous time, xp is discrete time, so their Fourier transform is non-periodic and periodic. Or you can think that because of the convolution, they began to overlap. So let me draw on over here one more time. So remember, this is actually convolution. So when you have a frequency, say that this is their signal. Just an example. Don't have to be those triangles, just an example. If you have an impulse spaced by omega s in frequency, when you do the convolution, remember, we pick one of them, just leave it like that, and then the other one, flip it and begin to sweep from low value to large value. So if you pick this one to sweeping coefficient, if they are symmetry, so even though you sweep, that's not matter. If you reverse it, that's not matter. And when you sweep from the lower side, say that this one comes to here and begin to, when this one is here, just forget about this one right now. Just focus on this yellow. When this one is here, then nothing comes out. When this one is begin to enter this region, for example, like that, same amplitude, then their multiplication will be same to the amplitude of this triangle signal, right? That's the reason that, and then next one comes in, this one comes in and do the same thing. That's the reason that they are repeating. They begin to repeat a triangle looks like. Of course, because scale, the amplitude is slightly different, but their value is quite similar. I mean, their shape is quite similar. What if that's the case that I started from the assumption that when you talk about this yellow, this one does not have any influence. That's our assumption. We just forget about it, right? That assumption is based on that. For example, how to say? In here, when this yellow began to enter, this reason, this second, say this is number 1, this is number 2. Number 1 began to enter. This number 2 is outside. This number 2 is already outside of this reason. One more time, this is important. We talk about that when this number 1 enters and begins to multiply, then our assumption here is this one doesn't have any influence. That's our basic assumption, right? To do that, if you're focusing only 1 and 2, that means when this number 1 begins to enter the region of non-zero, then number 2, if number 2 is here, then we cannot ignore number 2, right? We have to multiply number 1 with this, multiply number 2 with this, and have to add them together. However, if number 2 is here, which is outside of this band, then number 2 does not have any influence on this multiplication. Is it right? If you don't understand, you better ask now. All right. So basic assumption here is, you may think that the spacing between 1 and 2 should be larger than the spacing in here. Remember, we are talking in frequency domain, not time domain, right? This is frequency domain, not time domain. Meaning that here and here. So what we draw as triangle as a basic signal is sometimes we call the band limited signal, meaning that we can define their maximum frequency. That's why we talk about. Of course, if this is real, then we don't have to worry about that. But it sometimes has a minus sign. However, what this one says here is this value is from 0 to certain frequency. Doesn't have frequency larger than that. So this one is sometimes we refer as band limited signal because we can define the maximum band of this. What is the maximum frequency of this? And this one, from here to here, what is their spacing? We define here as omega s. What is omega s? In time domain, we're starting from, this is time domain, we're starting from our impulse train in time domain. Space equally spaced by time interval t. For this one kind of period or sampling period. Omega is what? 2 pi divided by t. Right? In here, they are spacing by t. Reverse of t is what? Frequency. 1 divided by t is frequency, f. If you change f to omega, you should multiply 2 pi to change from hertz to radian per second. So when you have t, which is time interval in time, then the frequency, which is the reverse of t, which is f, you multiply 2 pi to make f to w. I'm sorry, omega. So This one is called sampling period. This one is called sampling frequency. Sometimes we refer to as, this is actually sampling frequency sometimes, but in here let's use W. So from this assumption, the spacing between, now we go back to the frequency. In frequency domain, this 1 and 2, spacing between them in frequency is omega s, sampling frequency. Let's assume that this band limited value, the maximum frequency of the signal is W maximum. That means from here to here, let's assume there's image is symmetric. What is it? 2 omega max, right? So those are 2 omega max, which should be smaller than the spacing, so that this one does not overlap with this one. So we can draw a basic rule saying that in case of band limited signal, which we can define the maximum frequency, 2 times frequency should be smaller than the sampling frequency. I think you already heard about that. This is Nyquist's theorem. You may hear that, okay, signal has a frequency omega, sampling frequency should be at least 2 times larger than that. That's a Bayesian rule like that. There's many ways we can think, this is a more like a engineering way we can understand, just draw the picture and then see that there's spacing like that. There's a reason there's 2 over here, and there's a reason that it should be larger. This one also you can understand in the way we showed before. Let's go back to our previous example. I explained that this T is sampling period. As the reason that we cannot distinguish this signal is because the value between those sampling period we don't know because our sampling period is too long. So to solve it, we have to make sampling period shorter, meaning that we have to increase our sampling frequency. There's also corresponding to this criteria. This one tells you that sampling frequency cannot be smaller than certain value, at least larger than 2 times of largest frequency of the signal. But that's a minimum rule. To get a better data, you have to have 5 times or 10 times larger than the sampling the original value. Okay? So from here, if they happen to mistakenly designed, so if they happen to be that omega s smaller than 2 omega max, those one, when this one number 1 began to enter, number 2 is still there. So the resulting multiplication is not like the same shape, but somehow overlap. Because they should go to 0, that's not perfectly escape. This one does not perfectly get out from the area, so still there's some value. So when you have a kind of no overlapping, when this one and this one does not overlap, then we can find a train of impulse, a train of signal, which is quite similar to what is original value. But if you have overlapping, then it cannot be. We can also think in the way that as a result of the transform. So in case of discrete time phase transform, when you have it, they are periodic, so there should be omega. Now we are doing the omega s, which is sampling period, so their period in frequency is omega s. This is their max. This is their omega s minus omega max. Right? So to avoid overlapping, omega s minus omega max with this point should be larger than omega max. Is right? To avoid overlapping. When they began to overlap, then signal began to distort it. This, and after calculation, 2 times omega max, which is same to here. So you can understand either way, so that the train does not begin to follow those reasons, or the resulting periodic signal does not have any overlapping. You can think either way. In either way, if in case of band limited signal, the sampling frequency should be at least 2 times larger than the largest frequency of the signal. So what we do it? Why this one is important? How we can reconstruct the original signal. So you keep on, remember, this is our original signal, which is band limited by omega m, omega max. When you do the discrete time signal conversion by multiplication, we have learned by far, there will be a periodic by spacing of omega s. That's what we have learned. And then, how we can find this original value? How we can find from here, from this converted signal, how we can find this original signal? If you have this kind of low-pass filter, amplitude of T for scaling purpose, then we can just take out the central one to get the original one. Right? However, if you have, so why the overlapping is really matter? Because in this case, if you use low-pass filter, you can take out original signal. If you use low-pass filter in this case, there's no way you can take out the original signal. Right? That is the reason. That is the reason that the not overlapping is very, very, very important. So, in short, sampling theorem is called as Nyquist theorem, or sometimes called as Nyquist-Shannon theorem, sampling theorem, which is if X is band limited signal, which has a maximum bandwidth, maximum frequency omega m, then the sampling frequency should be larger than 2 times of the signal's maximum frequency. So there's Nyquist. So often you may hear just Nyquist theorem, or often sometimes people say Nyquist-Shannon theorem. But we like short word, so you may hear Nyquist theorem before. Okay, questions? So let's talk about sample. Now we switch topic. So now we switch topic. Before we move on, question, really, please. No? All right. So let's go to another topic. We briefly talk about that. How do we go back to original signal? So in here, I briefly mentioned that we first convert continuous time to discrete time signal, and then go back to continuous time signal by passing through a kind of filter, just passing through a low-pass filter, right? That's the process over here. So we will talk about, we will briefly talk about how to go back. So by far, we talk about converting from continuous to discrete. Michael's theorem talk about the sampling frequency, which how nicely we can change from continuous to discrete time. From now, we briefly introduce how we go back from discrete time to continuous time. All right? So let's go back to our previous example in the beginning of the lecture. Let's say we have this kind of discrete time signal, which we don't know what is original signal. So of course I draw in wrong way, but they are equally spaced in time. This is time domain. If you just intuitively thinking, if you are asked how to connect these 2 points, what is the first thing you want to try? Draw a line. Right? Of course, some of you don't like this, that you want some unique things. I want to like a round thing, like up and down, up and down. It's up to you, doesn't matter. But what I'm saying now here is, it's basically very similar. How to, in case of discrete time signal, they are discrete in time. So we don't know value between sampling period. We don't know the value over here. How we can estimate the value over here? Simplest way is just draw a line. Even simpler way is, okay, we just hold the data for until here, change, hold, change, hold, change, hold, change, hold. That's even simpler, right? This mechanism shown in white is called a zero hold. So take a value and hold, take a value and hold. So if you see this example over in the picture, say this is our original signal, and after sampling, we just try to take the value, hold, take a value, and then take a value, hold, take a value, hold, take a value, hold. And there will be, looks like this impulse, a kind of impulse-shaped value, which is of course different from original value. But if you make the spacing very finely, if you make the space very narrowly, then they are close enough. Similar to our integration. In case our integration, if you have a data like that, you try to calculate the area underneath here and add the area and make the spacing narrowly to make this, the addition of this area is same to actual the integration. That's one of the methods we are trying. So very similar to that. If you make this like that, of course they are different from original value, but if you make the spacing quite good enough, which make the frequency, sampling frequency higher, then they become close enough. So that's called the sample zero and hold. That's one way you can do that. So in zero order hold signal, which is why they use the zero order? What is the order? Order often refers to that if you have x1, this is order of 1, x0, that means order of 0, and x2, order of 2, something like this. That's the order. So zero order means this. What is x0? That's like 1, like a constant, is it right? So in here, what zero order means, they are holding in zero order, which is a holding in constant value. Make sense? So what it says here is they're holding a value at a constant value, doesn't have a slope. Holding a constant value, having no slope. That's what they talk about in over here. They actually, after they're passing through a pulse like that. So say that it's the same to what we have done before. X is our original continuous time signal. P is impulse train. XP is after sampling, which is after doing the discrete time signal. So XP is shown here like this. And then we add one more system shown in time. Looks like frequency, looks like low pass filter, but it's not really low pass filter. They're in time, more like an impulse in time. If they pass through it, remember, that is system response. That is system response. So we have to do the convolution. Is it right? We have to do the convolution when they pass through a system. So when you do the convolution of this and convolution of that, keep this one as it is, make this one reverse. So there will be a pulse like that and begin to sweep from low to large value. Then what happens? If there is a kind of rectangle over here, That's a good question actually. So, so question is, this one is after sampling. So, why we have to call them as T? Why do we have to call them as T? That's right. Actually, we can use NT instead. We can so in here we say XPT. I think that I just following the book, our notation in the book. I guess one of the reasons we are using here is for continuous, for unify the equation. That's what I'm guessing. Because you can, of course, because the data does not exist, the point other than that. Right? So you can just say that xn and say that, okay, our sampling is t, but you need to specify this information. If you specify information together with that, it's possible. But I think it's sometimes misleading because if just write xn, then n may be any arbitrary value, but it is not. We try to plot t and n together in same domain. So they just intentionally, I think, using the same thing. But actually, you're right. They should be shown like this or like that. So if you have, let's go back to here. Other question. If you have an impulse and then reverse the thing over here and begin to overlap until they reach here. That means from this point to this point, they are multiplied by this value. Is it right? So I should redraw it. This is discrete time signal. I should redraw it. If you multiply with this rectangular, when they begin to approach here, then they begin to multiply by this. They begin to multiply like that. They begin to multiply, continue to multiply this until they begin to hit here. Right? In here, they put t. Same with the spacing of that. Is it right? So the length in time is not this one began to enter this region, begin to multiply like that, and then they will keep on multiplied until they reach here. Right? From this point to this point, from here to here, they are same to here. And then when this one enters this region, note that this is same to this region, then they multiply by this, not by this. So they are holding like this. So if you pass through this specific system, then you can do the holding systemically. That's what they talk about over here. So this is one way we can represent our original value using discrete time signal. So this is zero hold. We are using zero order, just holding as constant value. But as you can intuitively say, we can make a draw line. Those line has a slope, and those line is not bound. So they are, you can think them as they are okay. Y equals a constant times t, which is x plus b, something like this. This one order of one. So we are talking about now the first order hold, which is we began to draw a straight line between 2 points. That's why you can see this example, sometimes called as linear interpolation. It's saying that we are connecting adjacent next data using straight lines. That's what you can see in here. Of course, if needed, we want to have, as you can see, this yellow one, white one is a kind of not so smooth, pretty sharp. That if you want to have more smoother way, what you can do is you can have instead you can connect them by y equals a t twice b or a t 3 times b, something like this. Because second order, third order, which we call the higher order, they are more round. So they will be looks like, all right, they will looks like this, they will looks like this, which is more smoother to connect them. But as you can imagine, we need more complex system to do it. That's a major thing. So that's pretty much over it in this lecture, except I will show you 2 examples about aliasing issue. We showed only one example, say that from zero hold, how we have to build a system to make zero hold. One example is we implement a new system in this box holding for certain t, and when they pass through the discrete time signal pass through, they become continuous time signal, which is not really smooth thing we expect to have, but one of the good estimate. This may be enough. If you don't like it, if you need a more accurate value, you should increase the order. One way you can increase the order here is you can either connect them using straight line or connect them using a round line, which is a higher order system. We did not cover what kind of system we need to do those higher order interpolation. They are explained in our textbook, so if you're interested, take a look at it. However, what I can say now here is this is needed to be a first order hold. Now they become much more complicated, right? So in short, there's nothing, if you want to increase if you want to increase your order of interpolation, you have to have different system having more complexity, which explained in the textbook. So if you want interest, take a look at it. But we only covers one example, which is zeta whole in this lecture. Questions? Ready? Okay. So let's try to finish the lecture by after this. So keep in mind, we have used effect. We're starting from continuous time signal, sampling, change to a kind of discrete time signal, and then using a new system called interpolation, or to go back to again to continuous time signal. So the example shown in here is, let's think about, let's summarize them. We have xt, which is continuous in time. After passing through one system, basically multiply by those train, impulse train, they change to a kind of discrete time signal, or kind of. Well, I say a kind of because according to your question, this is looks like a continuous time, but actually they are discrete time. So, and then we use a new system called H to go back to continuous time. We call recovered data. So we talk about those three data. And then we learn about Nyquist theorem, say the maximum frequency is omega n. The sampling frequency at here, which is omega s, should be larger than 2 times omega n to escape those overlapping. And why we have to escape overlapping? Because when you have overlapping, after you passing through this reconstruction algorithm, then this reconstruction signal is not the same with our original data when the overlapping happens. That's why we talked about before. So this is basic, the system, a very basic system we talk about now, right now. And let's take a look at one more example about it. So let's start from our example shown on the screen. This is case that xt, which is shown in here, is cosine omega 0 t. Let's assume that we have this is our input to the system. You may remember, I think you began to remind yourself again when you're preparing final exam, but in frequent domain, when you do the Fourier transform of cosine omega t, they are what? They have pi in omega 0 and pi in minus omega 0. That's what they talk about. That's the Fourier transform of cosine omega t, which is shown on the picture over here. After passing through the multiplication, they becomes we have to move it. We have to move it because this one will repeat, right? This one will repeat. So to avoid some confusion, let's draw this one as yellow. So left one from your side is yellow, right one from your side is white. If you have a large enough spacing, if you have a large enough spacing, then it looks like that. That's the first set. And then the center of this one will be shifted by omega s, which is sampling period, and there will be the shift like that. Those are second set. And then likewise, if you go to negative side, they are shifted by minus omega s, which is, this is their third set. So basically this one shift by omega s, shift by 2 omega s, shift by 3 omega s. Likewise, shift by minus omega s, minus 2 omega s, minus 3 omega s. That's what you can see in here. This is the case that there's no overlapping. No overlapping, meaning that the maximum value over here, which is omega 0. In case of cosine omega is a good example that they are band limited signal, because in cosine omega their maximum frequency is omega 0. There's no frequency higher than that. So we know that their maximum frequency is omega 0. If omega 0, so we know that it's omega 0, and also we know that this is omega 0 because they come from the same set. So the value over here should be omega s minus omega 0. If omega 0 is larger than omega s, smaller than like that, which is meeting the Nyquist theorem, there is no overlapping. And then we can reconstruct this one after passing through a kind of low-pass filter to take this out in frequency. So this is okay, which is shown in ABC. From A to B, in the figure, this is a pair, this is a pair, and this is a pair. So there's no overlapping. Likewise, we just change the omega 0 a little bit. We just increase omega 0 for this case. So these two are pair. So omega 0 is actually the same to omega 0, but the value, say this is 30 degree, then this may be 60 degree, just increase omega 0, the value itself. Then still there's no overlapping, but they are close. If you keep on increase the value of omega 0, sometimes this one become larger than this, which become overlapping happens, which is what you can see over here. That looks quite similar, but let me draw in here. In overlapping happens, then we will have white in your right side, yellow in your left side. That's what our basic criteria. But those omega s, if this omega s is not far away, then white, which left side of this one happen to be here, white, which should be right side of this one is over here. So the first set is those two. Second set is these two. So this one and this one is one set, this one and this one set. If right side of this one is larger than the white one, then when you do the low pass filtering, it's impossible to remove this white, right? To remove this, you have to also remove this white. That's the reason that we cannot reconstruct the original data. That's the reason that we try to make sampling large enough. That's what they show in frequent domain using more practical example omega 0, cosine omega 0. So when you do the exercise in special lab, it's very interesting because when you happen to select the data too small, high frequency component begin to distort it. It does not come as they looks like. So let's say how they looks like. Let's see how that looks like. So when there is no aliasing happening. So before we move on, I would like to emphasize a name. This one, which began to overlap, which is problem situation, we call aliasing. Aliasing. That's how we call it. So you can see over here aliasing. Aliasing is we have trouble. The overlapping happens. That's the case. So let's go back to what happens in time. We talk about in frequency domain, right? We have to talk about frequency domain. Take a look at what happens in time domain. So this is cosine. This is cosine, right? So our original signal is cosine. So first example over here. This is the original value, which is the cosine. And then we take sample, we take a discrete signal equally spaced like that. So this peak arrow are our discrete time signal. And then this is the case that there's no aliasing happens. So what we can see now after discrete time is like this. And after passing through interpolation, we can easily reconstruct how it looks like. Because we know enough point. This is what we talk about the beginning of today. Today's beginning time. We have, if you have enough point, then we can easily find how they looks like. This is the case that aliasing happens. So remember in the figure, actually the spacing, which is sampling period, is the same, right? The spacing, the point of the picking point are actually the same. So our sampling frequency is the same. Difference here is both of them are cosine omega t. But this first one, omega 0 is smaller than omega 0 over here. This one is faster. Fast is changing, right? So this one has faster signal frequency. Omega m is larger than omega m over here. Remember, aliasing happens when sampling frequency is smaller than 2 times omega m, right? So in this case, omega m, which is the data frequency, is 2 times of it is much smaller than sampling frequency, meeting Nyquist theorem, no aliasing happens. So we can reconstruct original data. In this case, as we increase omega m, the data frequency, signal frequency, so omega m, 2 times omega m become larger compared to this. But our omega s sampling frequency is the same. So 2 times omega m become larger than omega s. So this one has overlapping aliasing issue. In this case, this is our cosine having faster frequency, and then we are picking values, which they show looks like this. If you want to draw a line, can you draw a line? No, it's impossible because you can go like that. They may be smaller, they may go like that because we don't know the data over here. We know the data in between. In this case, we don't know data over here. We don't know data over here. So very hard to find how it looks like. So this example is briefly shows you that what happens if aliasing happens. In aliasing happens, it's very difficult to find our original data because our sampling number of our sampling is not enough, meaning that our sampling frequency is too small. So a way to do that is you have to increase your sampling frequency. That's it for this lecture. And if you even more increase it, if this may be okay, but in this example, it's impossible to reconstruct how actually it looks like. So if they even more increase, in this case, maybe they find, okay, there's large one here, small there, so they may be able to follow somehow. If they looks like that, very fastly changing frequency, it's impossible to see how they looks like because we are picking up data over here, we are picking up data over here, we are taking data over here, which looks like they are shown like that. So when the system try to follow, they follow this line instead of this fastly changing frequency. So they cannot find the original value. That's what they show in here.